Hi, my name is Nick. I'm going to walk you through this multi-coupling alignment program. So this is primarily intended for alignment of turbines with multiple shafts, but can realistically be applied to any industrial shaft alignment where multiple couplings have to be aligned at once. The video consists of several parts, and you can see the links to the specific times in the video description and the pinned comments below. So first, I'll cover the background, the information about the program itself, how to set up Solver on your computer. Promise it's extremely easy. How to enter the information about the turbine or whatever machinery you're working on, and how to enter current coupling alignment data. Then I'll focus on working with the outputs of the program itself. So that's horizontal and vertical alignment moves, setting up and adjusting constraints as needed, possible outputs and some limitations, and actually run through a few examples of how this can be used. Once you get the hang of it, it's really quite easy to use and can cut down time on trying to crunch numbers using old clunky spreadsheets. You'll have more flexibility, a better idea of how the constraints impact this adjusted alignment, and be able to perform multi-coupling alignment faster, thus also minimizing cost. So what this program does is use linear optimization to suggest moves for your shaft supports, and that's typically bearings or pedestal shims. And this enables you to align multiple shafts at the same time. It does that automatically at the click of a button once you enter all of the required data. While it does provide suggested alignment moves, this program is not a substitute for understanding the basics of alignment and experience. It has limitations, and ultimately it's up to the user to work with it and find the optimal solution. As I mentioned, this is an Excel-based spreadsheet that uses Solver plugin that's preloaded in all recent versions of Excel. While you already have it available without the need for any external downloads, it's something that needs to be activated. So to do this, follow the directions in the instruction tab, which is the first thing you should see when you open up the spreadsheet. So first, you're going to click on File, then scroll down to Options, and select Add-ins, and go down to this Manage field. You should have Excel add-ins selected. There's a couple of different options, but Excel add-ins, click Go, and then you'll get this pop-up menu. Just make sure that there's a checkbox next to Solver. Mine's already here, but yours probably won't have it. So make sure this is checked. Click OK, and that's it. In order to see kind of where this program resides, right, it was already pre-installed in your machine, but if you go to this data tab over here, Solver is located right there. Now you won't have to actually go here for any alignment needs, but it's good to know where it is. Right here you could see a quick rundown of some instructions if you don't have access to this video on how to use the program and how to activate Solver on your Excel. So once you're done with that, we can move on to entering the information about whatever unit you're working on. All right, so here we have the unit configuration tab. Here you're basically going to enter information about what you're working on. The way it's set up is it's looking at several shafts, right? So shaft 1, shaft 2, shaft 3, shaft 4, 5, and 6, and couplings between them. So connection points A, then we have B, C, D, and E. And it's set up where there are two supports. So in turbine world, bearings, and shaft number 1 has bearings 1 and 2. Shaft number 2 has bearings 3 and 4. And then T3, T5, T6, T7, T8, T9, T10, and so on. What you'll have to do is enter the bearing spans, then the distance from the bearing to the coupling. These are all in inches. And then finally, the coupling diameter in inches as well. So for example, just looking at what this is, these are numbers for a GE D11 steam turbine. So the bearing span from T1 to T2 over here in the HP section is 228 inches. And then the distance from T2 bearing, So the support to the face of the A coupling is 28 inches. From T3 to A coupling, so on this end, 55.6 inches. And then the diameter of A coupling is 26 3/4 inches, and so on. You can obviously change all this data. If you have less than 6 shafts, that's okay. These can be left blank. They don't really impact anything if they're left blank. And finally, you could click on this reset button to zero everything out. I'm not going to because we're going to be using this for the demo itself. Once that's entered, you can continue on to enter the alignment data that you currently have. Okay, so this is the current coupling alignment data that you'll be entering. There are 5 tabs for this, one for each individual coupling. So I've got coupling A, coupling B, C, D, and E. All of the sheets they look exactly the same, and all the information in them is the same. You don't have to fill all of them out. If you don't have, for example, C, D, or E coupling, those could be left blank and should be blank if you don't have them. So just fill out what you have, and we'll see where that goes from there. So looking at this sheet, at the top, we have some just information and data to enter. So I've got date, unit serial number, prepared by, day shift, night shift, or field engineer name. And then over here, this kind of allows you to keep track of which alignment iteration this is. So you could say that this is, your as found readings, or after you've made 1 move, 2 moves, whatever may apply. And then over here, again, kind of on the same theme, it might be useful to write what your previous move was, so that you can track it and see how your moves are affecting the actual alignment that you're seeing. So this is where you enter the actual data. Keep in mind that all the readings are in mils, so it's thousandths of an inch, not millimeters. Up top, we have this row, which is the rim readings. So when you set up your dial indicator, going from one shaft to the other, this is what you're reading, or a bridge mic. And then over here, these readings are all face readings. So whether you're doing them with sliding parallels or feeler gauges, this is where your face readings would go, right? And the way you would do it is, so you read the rotor 0 degrees, top left, bottom right, turn the rotors 90 degrees, repeat the measurements, and fill out this table. It computes the average numbers right here. So you've got the averages of all the face readings, and then relative face readings as well, with the top being referenced as 0 for left, bottom, and right, also in terms of face. Over here, we've got a data validation table. This doesn't actually impact anything or feed into any other alignment means. This just gives you an idea to make sure that your data looks right. So top plus bottom should equal left and right, both on the face and the rim. As you can see, there's a slight difference on the face readings here, right? So they don't actually exactly add up. I did that on purpose. It's okay if that doesn't happen. The program will continue working. The numbers don't have to be perfect, but you should just make sure that your data is reasonable by looking here. And then finally, we have the second table, which is a direct, exact copy. This is just for verification. For example, if you want to run the rim one more time after you've done it the first time, maybe it doesn't come back to 0 or something like that, or it's just a second set of readings that you want to take to make sure that they're right. This table does not impact anything going forward. So again, this is more of a data validation table as well for yourself versus anything that feeds the alignment program going forward. So if we go down a little bit lower, there's a couple additional things here. So this would be for the mechanics to fill out, right? The indicator is mounted on, shaft number 1 and or on the shaft number 1 coupling, reading shaft number 2 coupling, and a coupling diameter so that you can get this information from the mechanics if you don't already have it. It's important to know that because obviously it impacts your rim readings. And then when you enter the data, just make sure that this is selected correctly, right? So this is where your indicator is positioned. So mounted on shaft 1 means that the indicator is, whether it's glued or the bridge mic base is sitting on the shaft number 1, and the plunger of the dial indicator or the actual micrometer of the bridge mic is reading on the periphery of shaft number 2. There's a drop down right over here, and you can pick which one it is. Just a quick note, sometimes depending on your screen resolution, this note will pop up and kind of block this. So try to play with the zoom settings over here, just so that you can click on it somewhere over here and select the right configuration. Over here, this table is purely giving you an English translation as to what your coupling looks like. Right, so faces open 1.75 mils on top and 1.5 mils on the left, and it also tells you what's going on with the rim here. This graphic representation is being fed directly from the first table, so this table up top, right, this is the one that matters, and then this is also what will later feed the alignment program itself, so don't change the numbers here directly unless you specifically want to. If you don't want to fill out the table up top, but you already have these, you can plug them in and it'll let the program run. And then just, right, to verify that this means something, so right now we've got shaft number 1 reading shaft number 2, and we've got shaft number 1 is 23.5 mils lower. If we switch this, so now we have shaft number 2 is 23.5 mils lower. Obviously it won't do anything to your face, but the rim will flip. So again, make sure that this is right. These numbers, by the way, realize that these numbers don't match. I'll use this for one of the trial examples that we'll run through. So right now it's just looking at this table, and then these numbers are slightly worse in terms of the coupling alignment that we'll use to see how the program works later on. So once A coupling is filled in, you can move on to B coupling, right? Like I said, all these sheets are the same. And then for this specific example, C, D, and E are blank. After you're done entering that, you can move on to this vertical alignment and horizontal alignment tabs right down below. The vertical and horizontal alignment tabs, these two tabs at the end, are the output of the program. So this is where the magic happens. So let's look at what we have on screen. Up top is essentially a copy of what you input in that unit configuration tab. So it's bearing spans and the distance from bearing to coupling and the coupling diameters. Again, just a repetition, that's fed automatically from that previous tab, so you don't have to re-enter this information. And then moving, kind of skipping this middle portion for a second, we look at our current alignment. This is fed directly from the previous 5 tabs for A, B, C, D, and E coupling alignment, and shows you where you currently stand. Right? Just note that the gray cells, it says here, do not edit. Don't edit the gray cells, only edit these yellow cells. So now going back up here, this explains the sign convention for all the different measurements. So for our face readings, a positive number indicates that the face is open on top, and negative means that the face is open on the bottom. So just looking at this A coupling as an example, it's showing a positive 1.8 mils, so we expect the face to be open by 1.8 mils at the top. And just a quick verification for A coupling, we see that so the inside numbers are our face numbers, and the bottom is negative 1.75 mils relative to the 0 on top. So we're open by 175 or 1.8 on top. And now going to the rim designations, these are a little bit more complicated, but again, once you get the hang of it, it becomes natural. So a positive number means that your even bearing is lower than your odd bearing. To put it kind of more simply, if you go back to this machine info tab and look at your unit configuration, a positive number is going to mean that your shaft on the left is going to be lower than your shaft on the right. So when looking at the A coupling, if you've got a positive rim number there, that means that T2 is lower than T3. Right, so looking over here, we've got a positive 23.5, meaning that T2 is going to be lower than T3. And if we quickly look over here, we see the bottom, reading on shaft 2, bottom is negative 47. So again, that means the shaft number 1 is lower and it's reading a negative number. So moving on to what's on this sheet, this is fields now that you can actually change. This max misalignment allows you to set your own tolerances for how much misalignment you're willing to tolerate. Standard G procedure is 1 mil of misalignment on the face and 2 on the rim, but you can change this to whatever numbers you want, and the program will take that into account. And then moving down here, these are your moves. So this is what the program will actually tell you to move your bearings. Let's look at bearings, right? So T1, T2, T3, T4 through T12. So this is shaft 1, shaft 2, shaft 3, and so on. And then in these cells, you can set the maximum amount of move that you're willing to do on each bearing. So it's set as a standard to plus minus 10. For GE units, that means you don't have to re-blue the bearings. But again, you can change that to numbers that are higher or lower. For example, let's say you don't want to move a bearing, you could just set these to 0, right? And now the program won't move T1. And then this column over here will give you the calculated move for what your optimal alignment should be. Moving further to the right, this will be your resulting alignment. So after the moves over here are performed, this is what you're going to get. Currently, right, we're not making any moves, so this is just reflecting your current coupling alignment, right? So resulting alignment over here, 1.8, 23.5. This is just literally reading off of here. And then this you can change. This is your coupling specification. So for this specific turbine, the faces are supposed to be parallel, so that's 0. And then shaft 1 is supposed to be lower by 27 mils than shaft 2. So that's reflected over here. The difference is, specification versus the resulting alignment. So this is listing your current misalignment as it stands right now. This 1.8 mils and 3.5 mils and so on. And then once you do you run the program, this will tell you how much to move the bearings. This puts in English what this field outputs automatically. So, all right, instead of talking about it, let's run it and see what happens. So all you have to do is click Run Vertical Alignment. You'll get this pop-up saying Solver found a solution, all constraints and optimality conditions are satisfied, so that's good. That means it ran successfully. Click OK. And so let's look at what we've got. So these are the proposed moves, right? They can be seen over here. So T1 is staying put. We're not moving that. T2 down 8.2 mils. T3 down 4, and so on. Now I know that we often can't make, tenths of a mil move, but again, this gives you more information. So if you're constrained on what shims you have or what you can and can't do, this gives you an idea, which way to round up or down. And then this is our current misalignment, right? This is our specification and then the resulting alignment. So we essentially see that it's a perfect, you can align the unit perfectly if you do all of this. One way to see kind of the quality of the alignment you're going to get is by looking at this number over here. So currently it's set at it's 0. That is the best that you can get. Essentially what that does is it takes the sum of squares of all of these misalignments. So let's say you can click reset proposed move. It'll zero out all these moves. So we can see right now the resulting quality is 20.9. Again, we want that to be 0. But what that 20.9 is 1.8 squared plus 3.5 squared plus 1.3 squared plus -2 squared. So you want that number to be 0. That means that your alignment's perfect. So let's run this again. It should give us the same numbers. And then one thing that you can do here, for example, let's say T1 and T2, you don't want to move. So this is where that experience and playing with the program comes into play. So let's say you don't want to move the HVIP section. So you set this to 0. And now you're only moving T3, T4, and T5 and T6 for the generator. So you can just click run it again, see what that gives you. So solver found a solution, all constraints satisfied. Great, keep solver solution, click OK. And now we see the new numbers. So T1 and T2 are 0, right? We're not moving them. But we see that our alignment got a little bit worse, right? So this used to be 0, it used to be perfect, now it's 2.6. And again, what that is the sum of all these misalignment squares. So your rim's a little worse, your face is a little worse, but it's still okay, right? It's within tolerance. And one thing that you can, just looking at these results, is you can see when the calculated move is up against this constraint, right? So against your maximum or minimum, that means that if you increase this, your coupling can only get better, right? Because you're loosening a constraint. So let's say it's pretty easy to move the generator if you're already doing it. So if I increase this to, let's say 20, this can only make things better. So instead of this 2.6, we should expect a smaller number. So if we run this again, 2.5, right? So not much of a change. It's just moved by half a mil. But let's see what happens here. Let's say you're okay with moving T4 a little bit more. Run it again. And we go from 2.5 to 0.8, right? So these significantly improved, and our faces are pretty good as well. So again, this is where the experience comes in. Play around with it, see what's reasonable, see what's not, and find what suits you best. So this was the vertical side. Now we can move on to the horizontal alignment. So this is the horizontal tab. It's set up exactly the same way. The only difference is obviously instead of up and down, now we've got left and right. So a positive number on the face indicates face is open on the left. Negative is face is open on the right. You don't really use these too much anyway because all of this is spelled out to you over here. But I guess the resulting alignment, you do look at these. So for this one, a positive number for the rim means that T2, your even bearings are right of your odd bearings. So your shaft number 1, for example, would be to the right of shaft number 2. And number 2 would be to the right of shaft number 3, and so on, depending on what you're looking at. And negative, it's the reverse. And then a positive number is move bearing to the left, a negative number is move bearing to the right. So looking at this, right, our resulting, we haven't made any moves yet. This is as the coupling stands now. Our current resulting quality is 84. So it's not great, right? We've got a misalignment of 7.5 on the rim here and 5 here. And this face is out of spec as well at 1.5 instead of 1. So let's leave this as is and run it. Okay, so found a solution. Everything satisfied. Great. Click OK. And we get down to perfection. But let's remember that on vertical, we set these to 0, so we don't want to move the HP section. So let's set these to 0 as well. Run it one more time. Okay, once again, found a solution. So far, so good. And our number is a little bit, our resulting quality is a little worse, but overall still pretty great. Now, just to show you what happens when you do get an error. So let's say we keep moving these down to 0. So sometimes you'll get an error when the constraints that you have don't allow for the coupling to work out. So you'll get this error message saying solver could not find a feasible solution. What this means is that you have two sets of constraints, right? The maximum misalignment and the maximum, bearing moves themselves. So it can't both have, these small moves and align your unit. And typically what you'll see is either the number over here will exceed your limit, so it's supposed to be 0, 0, but you're seeing a negative 2.4. So obviously that doesn't agree. Or you'll see a greater number in the misalignment. You'll see like a 2.5 here, or I don't know, a 1.5 on the face. So when that happens, take a step back, see what you can do. So let's see what happens if we do 5 and -5. Run it again, and we're back to, this is a slightly different message. So it found the solution that works. Might not be perfect, but it's the best that it can do with these constraints. And essentially, again, we're in spec here, and everything works here. Okay, so next I'll run through an example with that other set of numbers that's slightly worse. So the last thing I wanted to do was run through another example where we just essentially add another shaft. So now we've got 4 shafts in play. I just copied, all the information from shaft 3, all the bearing spans and distances to coupling to shaft 4. So now we've introduced the C coupling. And for the C coupling data, made up some numbers to kind of make it a not so well aligned coupling. So it gives us a little bit of a problem, kind of like in the real world where you have to make this work. So we've got a face misalignment of 5 vertical and 3 horizontal, and then we're off by 8 mils vertical and 11 mils horizontal. So let's see what this does. In the vertical alignment, right, the C coupling's new. Hold on, let me reset this entire sheet so our previous moves don't carry over. Okay, and our initial quality here, as you can see, 294. That's pretty bad. This is, the rim is way misaligned here, the face is misaligned. So these are all the old numbers from the previous example we went over, and then this is the C coupling. 0, 0 spec, and 5 on the face, and 8 on the rim. So let's, before we even start, if we're calling this, the HP and then LPA and LPB maybe in the generator, we know that it's easy to move the generator. So let's just put in pretty high tolerances here right away. Run it. Okay, so could not find a feasible solution, so we're still way off. The face is showing pretty bad. The rim is close over here, but at the max over here. So let's see where our constraints are. So both of these are constrained T1, T2, and it looks like T5, T6. And over here, no constraints, so the generator, changing this around won't make anything any better. So now we have to make a decision. Obviously, the almost 3 mils is not close enough to get away with it. So since the HP, you can move the shell. Let's move these up. And you see I'm increasing, oh, that's -20. Increasing these constraints where it's hitting. Let's see what happens. Okay, so still not good enough. Although significantly better. We go to 2 mils on the face, which is approaching it. All of our rims got worse, though, just the way that it figured out. We're constrained over here on T1 and then T5, T6. So this is the LP. So let's say we give it a little help. Or actually, this way we only have to re-blue one bearing. Let's run it. Nope, still not good enough. And this is getting pretty high. Maybe change this. Didn't make anything any better. Let's go back to -10. Let's change this one. Okay, there we go. So found a solution. So we're within our spec. You can go with these numbers. Again, we have the choice of maybe saying let's sacrifice one face. So if we were to do this again, reset the entire sheet, and hold on. There it goes. So this is our worst face. I'll make this 40 and -40 again. And then let's say we're willing to live with a 2 mil face on HPIP. That might help us a lot. Okay, not good enough. That's okay. And we said we were willing to move these. Okay, getting there. Well, actually, this is already on the cusp, right? So this is probably, it said that it couldn't solve because this is probably rounding down from, 2.04, something like that. But let's say we move this 20. Right, let's give it a little more room. All right, there we go. Found a solution. These are maxed out, and we've got a pretty decent solution. Again, this is even better than we wanted it to be. Maybe change some of these, but in any way, you can see how you can play around with it and kind of say, okay, maybe I can sacrifice a little bit here so that my bearing moves aren't that bad. Right? In reality, 2 mils versus 1, you can probably live with that. And then go to horizontal. Let's run it and see what happens. Okay, I could not find, but it's actually pretty close. And constrained on this T8. That's the generator. Let's make it really large. And there we have it. This one actually came in pretty easily. So we're constrained over here, -30. That's a pretty big side-to-side move. And if you wanted to take that down, you could. And again, start playing around with it now that you kind of know the extent. So if we put it to -20, let's see. So this is 1, so this will get worse. Yeah, so this got worse, but you look at it, this makes it an easier move, and we're within spec on everything. So maybe this is what you go with. Again, considering you're moving the HP shell already, if you want to move your side-to-side keys as well, maybe you increase this and see what happens. It should help this face, right? So we put this to 15. Yeah, so this face went from 1 to 0.6. Is it worth it? That's really up to you. So again, this experience comes in with knowing how much you actually need. The system's always going to try to make it perfect. You don't always need it perfect. You just need it to be good for operation. So thank you very much for sticking through this. Hopefully this program makes alignments a little bit easier for you, right? We have a 4-shaft alignment that we finished in essentially 8 minutes. And if you have any questions or comments, please feel free to comment on the video or reach out to me directly. Thank you very much.